All right. Secant tangent, the other, and cosecant cotangent, the other popular substitution type situations. Little inconsistency with the font here if somebody wants it for a typo.
You know what? Yeah, I have 3 already. Oh, I do have 3.
Yeah, true.
Nice.
So in example 6, the idea is to be able to save a factor that you know is anti-differentiable. And I use the term anti-differentiable loosely because all of this stuff is anti-differentiable in that you can take its antiderivative using some technique. What I mean in this case is that it's using simple rules. Right? So something that would come from that formula sheet that I sent out on Remind. All right. So looking at this, I see secants and I see tangents. All right. We know that the antiderivative of secant squared is tangent. We know that the antiderivative of secant times tangent is secant. So if I can isolate one of those things, and in this case it looks like secant tangent, if I do that, then I should be in pretty good shape. Right? So I want to define a u that's going to allow me to cancel out the other part of the integral. Now, I don't have any rules that relate to a power of 4, but I do have rules that relate to a power of 2. So I'm going to write this as tangent squared squared. And then swap out the tangent squared for something involving a secant. All right? And again, these rules, they come from the Pythagorean identity of sine squared plus cosine squared is equal to 1. All right? So if I take sine squared and divide it, plus cosine squared equals 1 and divide it by cosine squared, I get the first rule. All right? So, or at least something similar to the first rule. All right? So that's telling me that I can rewrite this as secant x tan x instead of tangent squared, I'm going to write secant squared x minus 1. And I'll define my u as secant x, making du equal to secant x tan x dx. So a lot of things are going to cancel out here, or at least, well, actually one thing is going to cancel out, one factor, set of factors, but a lot of things are going to clean up nicely, right? So we're going to be looking at the antiderivative. The secant x tan x dx is going to get replaced with a u. The secant squared x minus 1 is going to become u squared minus 1 quantity squared du. Right. No fancy trig substitution or inverse trig or anything like that. Just simple distributive property. Anti-differentiate, 1/5 u to the 5th minus 2/3 u to the 3rd plus u plus c. And then reverse substitute. So bring back your secant, and you end up with 1/5 secant to the 5th of x minus 2/3 secant to the 3rd of x plus secant of x plus the c. When I was a student, I didn't buy into all these techniques until probably much later than I should have, because the first probably 3 or 4 days of instruction, all of the antiderivatives, they just kind of boil down the way that I suspected they would. So I'd be like, well, it looks like it's probably, this looks like it's probably the derivative of, and I would say, the square root of x squared minus 1. And then lo and behold, that's what it was. So it was basically guess and check. And that got me like most of the way. Until I got to problems like this, where it's like, yeah, nobody's guessing 1/5 secant to the 5th minus 2/3 secant to the 3rd plus secant plus c. Like, it's, okay, you can guess the plus c. But you're not guessing the other part of it. All right, so yeah, at that point, it's like, all right, well, I guess I got to learn all this stuff. Like, you could get probably 95% of the way to a correct answer with a guess and check. You look at a multiple choice question, you probably have a good sense, just going back to the exit ticket, you probably had a good sense just by looking at the choices which one was probably the correct antiderivative. But then justifying it was one thing, and also the odds that there was going to be 2 similar choices, those are very great. So you're looking at, or the probability anyway. So you're looking at 2 very similar ones. You're like, well, I know it's one of these 2. So unless you want to make a 50-50 on every single multiple choice question, you got to learn the techniques. Right? So that's where all this stuff is coming into play. Now, for the next one, it looks like we already have a secant squared, quote unquote, saved. So it's a question of, is that the right way to go? Well, what is the derivative of tangent? Secant squared. So if I take tangent and make that my u, that will cancel out the other part, all right? Because du would be equal to 3 times secant squared of 3x dx, but I only need secant squared, so it would be 1/3 of du.
How do you divide it by the number in the x term?
If you're taking the antiderivative, you do. It's a good question. So we're looking at u to the 4th to address the tangent to the 4th, and then 1/3 du to address everything else. In which case, and you can leave the 1/3 on the inside, it's not going to amount to much anyway. 1/15 u to the 5th. All right, so that's going to be 1/15 tangent 5 up to the 5th of 3x plus c. This is what I was talking about before, where I was saying guess and check can get you about 95% of the way. Because if I'm looking at multiple choices, my eye would probably jump right to this one, not because of the 1/15, but because of the tangent to the 5th. Because I see a tangent to the 4th in my integrand. I see one of my choices has a power of 5. I'm jumping right to that one immediately. Do a quick derivative and see if the derivative, because this is actually a very simple expression. Will the derivative of this give me that? I wouldn't go through any of this on the AP. Right? So, like demonstration of knowledge is one thing, but getting the answer quickly, that's the name of the game when it comes to the AP exam. Right? And those are strategies that we'll work on a little bit further down the line. Basically, we're going to take an AP exam together in class, just so we can go through strategies like that. Parts of it will be tedious. It's kind of like going over a test in class. It was like everybody got number 1 right, but we're going to go over it anyway. Be like, all right, can we just kind of jump to the ones that I got wrong? So, but we're going to really be focusing on strategies because your brain might take you in one direction, but I want to show you that there might be a better path for you to take. All right. So for homework, the only thing I'd like you to do is this bad boy right here, which works in cosecants and cotangents rather than secants and tangents. All right, so it goes back to the idea that, you know, like, do we remember all the rules or do we invent them on the fly? I don't know. So if you know the basic Pythagorean identity, sine squared plus cosine squared is equal to 1. You can create the other two from that basic identity. So, for example, you could divide everything by cosine squared, in which case you get tangent squared plus 1 is equal to secant squared. Or you could divide each part by sine squared, in which case you get 1 plus cotangent squared is equal to cosecant squared. All right, so instead of memorizing rules, maybe you do that. I don't know, or maybe you memorize the rules, it's up to you. But the idea with cosecant and cotangent, you have a relationship between them. So you might be able to save yourself a cosecant squared. If that's the case, you would do that because we know the antiderivative of cosecant squared. You might try to save a cosecant cotangent because, again, we know the antiderivative of that as well. Right? So we'll start with the simpler thing to do, which would be to save yourself a cosecant squared. All right? So if that's the case, I'm going to rewrite this as cosecant squared x times cosecant squared x times cotangent to the fourth cotangent. Jeez Louise. To the fourth of x. All right. Now, you have your rules. And one of the rules tells us that we can take a cosecant squared and replace it with a 1 plus cotangent squared. All right? So that's the one we just invented. So either one of them, we can make that happen. We don't want to do it with both because then we'll paint ourselves into a corner. So I'll just take this one for example. So cosecant squared x times 1 plus cotangent squared x times the cotangent to the fourth that's already there. A little distributive property. It would be cotangent, and you actually don't have to distribute. We did something similar to this last class, maybe 2 classes ago. Cotangent to the fourth x plus cotangent to the sixth x dx. The idea being that I could define a u related to the cotangent. All right, and that's because we know tangent has a derivative of secant squared, so cotangent has a derivative of negative cosecant squared. That's going to help us cancel out the other part of the integral. All right, so negative cosecant squared x dx. We don't need the negative, so we'll negate both sides. Negative du is equal to cosecant squared x dx. So we'll be looking at, we'll have a negative, a du, and instead of cotangent to the fourth plus cotangent to the sixth, it'll just be u to the fourth plus u to the sixth. Now my du's a little too far away, so let me bring that in. Now it's just simple reverse power rule. So we have the negative. I'll put some brackets, I like brackets. 1/5 u to the fifth plus 1/7 u to the seventh, all plus c. Reverse sub. You have 1/5 cotangent to the fifth of x plus 1/7 cotangent to the seventh of x, all plus c. Or you could distribute the negative if you want. Not necessary though. All right. The kind of thing where, you know, you probably could check it by distributing. Sorry, differentiating. You could probably check it with the calculator. Calculator's a little iffy because you never know if you're going to have the ability to use the calculator, so it may not be worth it. But do you want to take the time to differentiate this to see if it ends up equaling that? That's a question only you can answer, I think. Right? It all depends on how much time you have left on the test or on the AP. You know, if you're staring at the clock and there's like 20 minutes left, you're like, oh, well, I got nothing better to do. You might as well. If that's not the case, then you're like, okay, looks good. Moving right along. And, you know, of course, if it matches up with a choice, you're probably satisfied anyway.
So, the kind of like the first step where you knew to change like cosecant to the fourth x to like cosecant squared x times cosecant squared x and then sub in an identity. What would happen if you like didn't think to do that at first and you tried like maybe trying to sub in or like saving a cosecant of x, cotangent of x, or like trying to convert the sine to cosines?
You could get there still, eventually. It would just be more roundabout. Like if you did the cosecant, cotangent, if you save that, then you would have cosecant and cotangent as powers of 3. So then you'd still have to save another cosecant, cotangent, and then convert over the cosecant square, cotangent squares, well, one of them anyway, and then try to clean it up from there. It could bring in a big circle, or it could eventually work out, but I think it's going to be a more roundabout approach. When you go to sines and cosines, it could simplify things. You know, in this case, let's just take a quick look. It would be 1 over sine to the 4th times cosine to the 4th over sine to the 4th. So cosine to the 4th of x over sine to the 8th of x dx. Usually at this point it's like, well, it's not looking so good. But then you'd start getting into other identities maybe to try to simplify things out, right? So if that's the case, you might be thinking like,
What about u substitution in that?
in that case, the thing with u substitution is if you define u as sine, that'll cancel one of the cosines, but not all 4 of them. If you define u as sine to the 8th, that's going to give you 8 times sine to the 7th of x times cosine. So it's still only going to cancel one of the cosines and introduce more sines.
Equals sine to the 5th x?
If you do u equals sine to the 5th of
Oh,
x,
sorry. Yeah.
well, that would help you cancel out the cosines, but you still have 3 powers of sine left over. So
all these ones is like, it's not that they couldn't work.
it's that it's
like,
more
this
work.
is more efficient.
This is the more efficient approach, exactly. Yeah.
For the dx, is that a value or is it just kind of there?
At this point, we're just saying it's there to
Okay.
represent an instruction telling you to take the antiderivative. In the next unit, you'll see exactly what its true role is.
Okay. Would you ever have to distribute it as like, because it's a value?
Really only in the context of solving a differential equation, but for these kind of problems, no.
Oh.
And it'll in the next unit, we're going to see what role the dx has in developing the area under a curve, and it'll make all the sense in the world. But I've gone both ways with that. I've taught it where we've gone the area route first, and people are like, okay, cool, that makes sense, but how did you know the antiderivative of cosine was sine? You know, like, and it's like, I kind of settled on the idea of like, let's just get the skills out of the way first, and then we'll get into the theory. All right. Okay, so that's the